Imagine if you could be in two places at the same time. Sounds like a fantasy, right? But in the world of quantum mechanics, this isn't just a theoretical possibility, it's a reality. Quantum mechanics is this extraordinary branch of physics that dives into the behavior of matter and energy at their most minute. We're talking about the realm of atoms and subatomic particles here. The rules of the game change at this scale, and one of the most mind-bending examples of this is the concept of quantum superposition. This principle suggests that particles can exist in multiple states simultaneously until observed. Yes, you heard that right. Until observed. It's as if the universe is playing a game of hide and seek with us, revealing its secrets only when we peek. So, welcome to the strange, yet fascinating world of quantum mechanics, where the laws of physics as we know them take a back seat. Quantum mechanics wasn't always part of our scientific knowledge. It had a birth, a beginning, sparked by a failure of classical mechanics. The dawn of the 20th century saw the world of physics in a bit of a pickle. Classical mechanics, the traditional physics of Newton, was falling short. It couldn't explain certain phenomena, like the behavior of light and the stability of atoms. The universe, it seemed, was not playing by the rules we thought it would. Enter Max Planck, a German physicist. He was wrestling with a problem known as the black body radiation problem. It was a puzzle of how objects emit radiation when heated. Classical mechanics predicted an ultraviolet catastrophe, a theoretical outcome that simply didn't match the observed reality. Planck, in a desperate move, proposed that energy was not continuous but came in discrete packets, which he called quanta. This was a drastic departure from what was believed at the time and marked the first step towards quantum mechanics. But the world wasn't quite ready to accept this new idea. It was Albert Einstein, yes, the very same Einstein of the theory of relativity, who gave Planck's idea a boost. Einstein proposed that light itself was made up of these quanta, which he called photons. This explained the photoelectric effect, another phenomenon that classical mechanics couldn't account for. Quantum mechanics began to take shape. It was a science that described a reality vastly different from our everyday experiences, a reality where particles could be in two places at once, where observing a system could change its state. The journey was far from easy. The pioneers of quantum mechanics faced criticism, disbelief, and even ridicule. But they persevered, driven by a desire to understand the universe at its most fundamental level. Their courage and curiosity gave us a new lens through which to view the world, a lens that revealed a universe both strange and beautiful. Thus, the stage was set for a new kind of physics, one that could explain the unexplainable, the quantum mechanics. Now hold on to your hats, because we're about to dive into the deep end of the quantum pool. Let's start with the principle of superposition. In the everyday world, we're used to things being in one place at a time. You're either in your living room or your kitchen, but not both. Quantum mechanics, however, laughs in the face of such simplicity. A quantum particle, according to superposition, can be in multiple states at the same time. It's like being in the living room and the kitchen simultaneously. But here's the kicker. We can't know which state it's in until we measure it. And the act of measuring forces the particle to choose one state. Cue the second principle, the uncertainty principle. Devised by Werner Heisenberg, this principle states that you can't know both the position and momentum of a particle with absolute certainty. The more precisely you know one, the less precisely you can know the other. It's like trying to juggle while riding a unicycle. The more you focus on one task, the more the other suffers. This isn't due to any deficiencies in our measurement tools. It's a fundamental aspect of nature. Next up is the concept of a wave function. A quantum state isn't defined by definitive properties, but by possibilities, each with a certain probability. These probabilities are encapsulated in the wave function, a mathematical function that provides the probabilities of the outcomes of experiments. But remember, until we make a measurement, the particle exists in all its possible states. Finally, let's talk about entanglement, or as Einstein called it, spooky action at a distance. When two particles become entangled, their states become linked. Change the state of one particle and the other changes instantaneously, no matter how far apart they are. This is a real head-scratcher because it seems to defy our understanding of how information can travel. All these principles create a quantum world that is strange and counterintuitive. A world where particles can be many places at once, where observing changes the observed, where uncertainty is certain, and where distant particles can be mysteriously connected. This is the realm of quantum mechanics, a place where the rules of the classical world are thrown out the window and replaced by probabilities, wave functions, and entanglements. It challenges our understanding of reality and forces us to accept a level of weirdness that seems almost magical. Yet, these puzzling principles have been verified by countless experiments and are the foundation of many technologies we rely on today, from lasers to MRIs to our future quantum computers. Baffling, isn't it? But these principles are what make quantum mechanics so powerful and so intriguing. You might wonder, do these strange phenomena have any relevance in our daily lives? Well, the answer is a resounding yes. Believe it or not, quantum mechanics is deeply entrenched in the technologies we use every day. Take lasers, for instance. They're not just for sci-fi movies or fancy light shows. They're used in everything from barcode scanners in your local supermarket to surgical equipment in hospitals. The principle behind lasers, of stimulated emission of radiation, is a direct application of quantum mechanics. Then there are semiconductors, the building blocks of our digital age. The computers you use, the smartphone in your pocket, even the humble digital watch, all rely on semiconductors. These devices use the quantum mechanical behavior of electrons to function, and it doesn't stop there. Ever had or know someone who's had an MRI scan? That's magnetic resonance imaging for the uninitiated. This powerful diagnostic tool leverages the principles of quantum mechanics to create detailed images of the body's internal structures. In an MRI machine, the nuclei of atoms in your body are excited by a strong magnetic field, causing them to emit radio waves, which are then used to create the images. See, quantum mechanics isn't just about puzzling principles and mind-boggling phenomena. It's a science that's deeply woven into the fabric of our everyday lives, silently powering the technologies we rely on. Without it, our world would look vastly different. We'd be without many of the technological advancements we often take for granted. No smartphones, no high-speed internet, no advanced medical imaging. So the next time you use your smartphone or see a laser in action, remember, it's all thanks to the strange and wonderful world of quantum mechanics. It's not just a surreal science, it's a practical one too. So unbeknown to many of us, quantum mechanics plays a crucial role in powering our modern world. The quantum world might seem far removed from our everyday lives, but that's about to change. As we venture further into the 21st century, we're beginning to see the emergence of a new era, one dominated by the principles of quantum mechanics. The quantum future, as it's often called, is no longer just a theoretical concept. It's a tangible reality that's shaping up right before our eyes. One of the most exciting developments in this quantum future is the advent of quantum computing. Traditional computers, as we know them, use bits which can be either a 0 or a 1. But a quantum computer isn't limited to just two states. It uses quantum bits or qubits, which can be both a 0 and a 1 at the same time, thanks to a principle known as superposition. This allows quantum computers to process information at an exponentially faster rate than traditional computers. Imagine solving complex problems in seconds that would take a conventional computer thousands of years to crack. That's the power of quantum computing. But the quantum future isn't just about faster computing. It's also about redefining the way we think about communication and connectivity. Enter quantum teleportation. It sounds like something straight out of a science fiction novel, doesn't it? But it's real. Scientists have already successfully teleported information between particles over short distances. And while we're still a long way from beaming people or objects across space, the implications for secure, instantaneous communication are immense. So, as we look to the horizon, we see a future where quantum mechanics isn't just a complex scientific theory, but a part of our daily lives, driving our computers, powering our communications, and perhaps even redefining the very fabric of reality as we know it. As we stand on the brink of a quantum revolution, one thing is clear: the future is quantum.